The brightest galaxy ever seen glows with a force that almost feels unnatural. Across the abyss of cosmic dark, its light reaches Earth after billions of years of travel, burning with an intensity that defies ordinary comprehension. Astronomers measure it not in the simple count of stars, but in magnitudes of power. Its radiance outshines entire clusters, as though a trillion suns had been compressed into one piercing beacon. To look upon its data is not merely to observe. It is to feel the weight of energy released at scales the human nervous system was never built to grasp. And yet the mind, fragile though it is, bends around the enormity, struggling to render such immensity into mental imagery. This galaxy, catalogued not as a name, but as a sequence of numbers and letters, stands as a marker in human inquiry. Its brightness is not a casual glow, but a furnace of cosmological violence, where gravity tears matter apart and transforms destruction into light. To contemplate it is to press against the boundaries of perception, where human senses fail and instruments extend the reach of consciousness. But the brightness itself is not the whole story. In psychology, brightness is more than photons. The eye captures contrast, the brain amplifies signal, and awareness itself can distort what is perceived. Ancient texts, from the Rig Veda to the writings of Plotinus, spoke of divine radiance not as an external fact, but as an interior event. Illumination as awakening. Neuroscience echoes this metaphor. When subjects in altered states, whether through sensory deprivation, breath control, or deep trance, describe visions of blinding light, functional MRI scans show hyperactivity in visual cortices, even when the eyes remain closed. The brain, in other words, is capable of generating its own galaxies of fire. The brightest galaxy ever seen, then, becomes a mirror of two domains, the physical and the psychological. Out there in the cosmic distance, it is a real object, catalogued by telescopes, red-shifted by expansion, luminous beyond calculation. But within human awareness, its discovery triggers a subtler process. The mind translates raw data into image, image into metaphor, metaphor into a kind of inner radiance. The brightest galaxy is not just far away, it also burns in the folds of imagination, where neurons spark with their own version of cosmic light. Experiments in sensory perception reveal how fragile brightness is as a measure. In 1965, Cornsweet and Pinsker demonstrated how edges and contrasts can make identical surfaces appear different in luminance. What we see as bright may not be brighter at all, but merely more exaggerated by context. The universe works similarly. A galaxy of ordinary size, when fueled by a black hole's hunger, can masquerade as the most luminous object in the cosmos. What is seen is not always what is real, an illusion both optical and cosmological. This duality between perception and existence shapes how science communicates discoveries. For the astronomer, the brightest galaxy is an entry in a table with flux measurements and uncertainties. For the public, it becomes a glowing giant, a lighthouse of creation. For the mystic, it is proof of divine fire scattered across the heavens. The truth hovers in between, photons striking a sensor, transformed by algorithms into color, then by neurons into awe. Consider how the mind reacts when told of brightness that exceeds trillions of suns. It cannot truly hold the number. Instead, it defaults to metaphor, the eye of God, the torch of eternity, the mirror of infinity. Psychologists such as George Miller pointed out the limits of working memory, the magical number 7 plus or minus 2. Beyond that, humans rely on grouping, on compressing data into symbolic units. In this way, the brightest galaxy becomes less about astrophysics and more about the architecture of cognition. We compress, we symbolize, we render unthinkable magnitude into graspable illusion. And yet, the illusion carries weight. Placebo and nocebo studies reveal how belief alters physiology. Light, even imagined, triggers measurable shifts in brainwave frequency. Meditation practices that focus on inner luminosity, whether the Tibetan clear light or the Christian Visio Beatifica, show increased gamma synchrony, as if neurons align themselves into coherence under the spell of imagined radiance. To think of the brightest galaxy is not passive. It stirs hidden circuits, sharpening focus, altering breath, even slowing the sense of time. Astronomers did not seek mysticism when they found this galaxy. They pointed their instruments outward, not inward, but the result crosses boundaries. Just as cosmic light traverses billions of years to reach a human retina, psychological light traverses neural circuits to shape consciousness. The two realms converge in the act of perception. The brightest galaxy ever seen is, in this sense, not only a distant object, but a neural event happening right now, in the reader's brain, igniting networks that cannot help but simulate brilliance. And still, despite the metaphors, the data remain stark. This galaxy's photons have traveled since long before Earth bore life, piercing epochs of cosmic silence. The brain that now interprets them is the product of evolutionary chance, adapted to forests and firelight, now straining to interpret scales that dwarf imagination. The nervous system responds with awe, confusion, and subtle unease, the sense that behind the light lies a force too large, too consuming, too absolute to ever be reconciled with ordinary thought. Such unease is not unfamiliar. Ancient humans, gazing upward, marked the brightest stars as gods, their radiance inseparable from authority and fear. Modern instruments strip away myth, yet the reaction persists. To measure is not to tame. Even calibrated brightness, expressed in ergs per second, feels uncanny. And as with all uncanny perception, it alters the rhythm of breath, the tone of thought, the weight of silence. What lies behind this brilliance, what mechanism fuels it, remains to be traced. Yet already the discovery unsettles perception, blurring the line between what is not static ornaments, what is imagined in the void, and what is believed. They are engines of light and matter whose brightness is both a clue and a deception. Their glow reaches across space because of two primary sources: the cumulative output of their stars and the violence of their central black holes. To understand brightness at the galactic scale requires peeling apart these layers, separating the gentle radiance of stellar populations from the searing brilliance of gravitational collapse. The stars provide the first foundation. Each galaxy carries billions, sometimes trillions of them, each releasing energy by fusing hydrogen into helium. Individually, a star is modest, a point of light. But multiplied across a galactic disk, their output becomes extraordinary. Astronomers quantify this in terms of luminosity functions, noting that spiral galaxies like the Milky Way shine with roughly 10 billion times the brightness of the Sun, while larger ellipticals can exceed 100 billion times. This measure, however, conceals variation. Young, hot blue stars radiate more intensely than old, red ones. A galaxy undergoing starburst, where clouds of gas collapse rapidly into new stars, can temporarily outshine its more quiescent peers by a factor of 10 or more. Brightness at this scale depends not only on how many stars exist, but on their age, composition, and distribution. A population dominated by massive, short-lived stars will blaze fiercely, yet briefly. One governed by smaller, cooler stars will glow faintly for billions of years. This relationship between stellar demographics and galactic light resembles the way human brains allocate energy. Bursts of rapid firing in neural assemblies produce momentary flashes of cognition. while the slow hum of background activity sustains awareness. Just as neurons in synchrony create mental clarity, clusters of young stars light up galactic arms, giving form and definition to what would otherwise be an indistinct haze. Beyond stellar radiance lies another, more violent source. In certain galaxies, a supermassive black hole sits at the core, surrounded by an accretion disk of infalling matter. Instead of disappearing silently, gas and dust spiraling into the gravitational well are compressed, heated, and torn apart by friction and tidal forces. Temperatures soar into the millions of degrees. At that point, energy escapes not as starlight, but as a torrent across the electromagnetic spectrum. Radio, ultraviolet, X-ray, gamma-ray, outshining all the stars combined. Galaxies with such active centers become quasars, their brilliance amplified by mechanisms that, in a paradox of physics, convert darkness into light. The existence of these dual sources complicates interpretation. Observers cannot look at a bright galaxy and know immediately whether its glow comes from stars, a black hole, or both. Instruments must separate the signals, analyzing spectra for fingerprints of starlight versus accretion. Where stellar populations reveal hydrogen absorption lines, accretion disks announce themselves through broad emission features, shifted and stretched by relativistic effects. To parse these signatures is to decipher a palimpsest, where one layer of brightness overwrites another, each telling part of the story. Brightness also interacts with perception through distance. Light diminishes with the square of distance traveled, yet the expansion of space stretches wavelengths, dimming them further. A galaxy may burn with ferocity, but by the time its photons reach detectors, their intensity is muted, their frequencies shifted into the infrared. Astronomers counter this with sensitivity. Arrays of detectors cooled to near absolute zero, lenses polished to atomic precision, algorithms trained to extract faint signals from noise. The brightest galaxies, even so, appear as smudges, their overwhelming energy reduced to a subtle rise in flux, invisible to the naked eye. What begins as cosmic violence ends as a fragile trace on a graph, vulnerable to interference and misinterpretation. The psychology of brightness enters here again, for human beings are not adept at intuiting logarithmic scales. To say that one galaxy is 10 times brighter than another means little without metaphor. Psychologists studying magnitude estimation, Stevens, in the mid-20th century, for instance, demonstrated that the human mind compresses differences in intensity. A light perceived as twice as bright might actually be tenfold in energy. At galactic scales, this distortion becomes even more pronounced. When scientists report that a quasar shines with the power of 1 trillion suns, the figure is mathematically precise, but cognitively void. The brain cannot build a sensory equivalent, so it defaults to awe or disbelief. Cultural responses to brightness have always mixed precision and awe. Ancient Mesopotamians ranked stars not only by position, but by magnitude, long before telescopes, assigning mythic roles to the most luminous. Chinese astronomers tracked guest stars, supernovae, that briefly outshone planets, recording events that matched across centuries and civilizations. In medieval Europe, light itself became a theological category. Lux versus lumen, divine radiance versus earthly glow. To speak of a galaxy's brightness in that context would have been to attribute to it not only physical power, but spiritual consequence. Even stripped of theology, the resonance remains. Extreme brightness continues to evoke the sense of contact with forces beyond comprehension. At the physiological level, brightness strains the eye. Experiments on photic stimulation, such as those conducted in the 20th century on flickering light, show that intense brightness modulated at certain frequencies can induce altered states, visual hallucinations, shifts in time perception, even out-of-body sensations. A galaxy too far to burn the retina nevertheless provokes the same neural machinery when imagined. The difference between photons striking cones in the retina and mental imagery generated in the cortex grows thin. What overwhelms the senses in the external world can be mimicked internally, hinting at why reports of radiant visions appear across mystical traditions, from the blinding light of Saul's conversion on the road to Damascus to the descriptions of bodhisattvas in Buddhist sutras. Brightness, then, is both astrophysical measurement and psychological trigger. It reveals mechanisms of matter and gravity while exposing the limitations of perception. The brightest galaxies show the extremes of energy release, but they also demonstrate how human minds translate extremes into images, myths, and altered states. Behind every measurement lies this double register: physical fact intertwined with cognitive illusion. And yet the question persists. When a galaxy blazes millions of times more fiercely than the Milky Way, what specific discovery made its presence undeniable? And how was that trace pulled from the silence of space? The answer resides not in theory alone, but in the meticulous work of observation, where fragile photons carry the history of violence and creation across unfathomable distances, waiting to be recognized.
The search for extraordinary galaxies begins not with a single telescope fixed on a patch of sky, but with wide-field surveys designed to harvest light from millions of objects at once. Each image, stitched from long exposures, becomes a catalogue of candidates whose faint signatures must be sifted with care. The discovery of the brightest galaxy emerged through this methodical trawling of the heavens, where pattern recognition algorithms scanned for anomalies that human vision could not reliably detect. It was not brilliance visible to the naked eye that singled it out, but an excess of energy buried in data arrays, a statistical spike demanding closer inspection. Modern astronomy relies heavily on such surveys because the scale of the universe dwarfs any one instrument's gaze. The Sloan Digital Sky Survey, for instance, mapped hundreds of millions of celestial sources, each tagged with coordinates, flux values, and spectra. When astronomers later identified the luminous beacon, they did so by cross-matching these enormous databases, searching for outliers whose infrared brightness exceeded ordinary galaxies by orders of magnitude. Infrared was crucial, for light from such distant sources has been stretched by cosmic expansion until it no longer registers in the optical band. Only detectors tuned to longer wavelengths could catch the faint residue of brilliance that began its journey billions of years ago. Once flagged, the candidate galaxy required verification. Multiple telescopes, scattered across continents and orbiting in space, trained their instruments on the same coordinates. The Herschel Space Observatory provided crucial measurements in far infrared, while ground-based observatories in Chile recorded millimeter-wave emissions tracing cold dust. Each dataset, when layered together, revealed a source whose luminosity was not a miscalibration or noise artifact, but an authentic release of staggering energy. The process resembled assembling a mosaic from shards of glass scattered across the floor of the cosmos, each shard a different wavelength, each contributing to the image of a singular object. The light itself carried history. Its photons had departed when the universe was a fraction of its present age, long before Earth existed. During that journey, they encountered no barriers, no interruptions, only the slow redshifting of space's expansion. By the time they reached the detectors, their frequency had fallen into the infrared, their intensity attenuated almost to invisibility. Yet the signal remained coherent, carrying spectral features that betrayed the processes that produced them. Emission lines from ionized oxygen, carbon, and hydrogen encoded the violence of star formation and accretion, hinting at temperatures and densities unreachable in terrestrial laboratories. The detection was not merely a matter of instruments, but of interpretation. Astronomers trained in spectroscopy could read those lines like archaeologists deciphering an inscription. The spacing of peaks, the asymmetry of profiles, the ratios of intensities, each detail pointed to mechanisms unfolding in the depths of that galaxy. Where laypeople might see only graphs of squiggling curves, experts traced evidence of shock waves, jets, and plasma outflows. The galaxy announced itself not by an image glowing on a screen, but by patterns of energy demanding recognition. Such recognition, however, is never free of uncertainty. Statistical methods dominate astrophysics because faint sources can be confused with background noise. To establish certainty, researchers calculated signal-to-noise ratios, cross-referenced independent instruments, and submitted findings to peer review. The brightness of the galaxy had to withstand scrutiny from multiple angles. Only when infrared luminosity exceeded 10, 14, 10, 14 solar outputs, a value nearly incomprehensible, did consensus begin to settle. This was not a misidentified starburst or a nearby object masquerading as distant. It was, by every test, an extreme galaxy shining across the eons. The psychological impact of such discovery mirrors the cognitive dissonance studied in other scientific domains. When evidence points to a scale beyond habitual comprehension, the human mind often resists, seeking more familiar explanations. Leon Festinger's theory of cognitive dissonance describes the discomfort when belief and evidence diverge. In astronomy, the discomfort arises not from contradiction but from immensity. The data insist on energy releases so vast that no terrestrial comparison suffices, producing a kind of epistemic vertigo. Scientists, trained to handle numbers, still feel the weight of that dissonance. To reconcile it, they transform the figures into metaphors: lighthouses, beacons, furnaces, knowing full well that the language diminishes the reality but provides a bridge for thought. Historical parallels abound. When Galileo first pointed his telescope at Jupiter and observed moons in orbit, the evidence challenged entrenched cosmologies. The discovery of a galaxy whose brightness dwarfs imagination exerts a similar pressure on contemporary frameworks. While no doctrine collapses outright, models of galaxy formation, black hole growth, and energy feedback must be stretched, recalibrated, or sometimes discarded. Scientific revolutions often begin this way, not with fireworks but with a quiet dataset that refuses to conform. The role of technology in these discoveries cannot be overstated. Charge-coupled devices, cryogenic cooling systems, adaptive optics, all serve as extensions of perception. Each advancement in instrumentation resembles the sharpening of a sense organ, granting access to stimuli that otherwise remain undetectable. The brightest galaxy exists in objective terms, but its recognition depends entirely on these prosthetic senses. Without them, the object would remain invisible, its radiance lost in the background, unknown and unimagined. The act of discovery, then, is not just about light traveling to Earth, but about human ingenuity building the means to intercept it. Yet interception does not erase strangeness. When plotted on graphs, the energy output spikes so far above baseline that it resembles an anomaly, a glitch in the system. Researchers double-check calibrations, repeat observations, and seek alternative explanations, yet the anomaly persists, confirmed rather than dissolved. Such persistence transforms anomaly into reality, but the sense of strangeness remains. The brightest galaxy is not domesticated by measurement. It remains a frontier of understanding, pressing against the limits of current theory. Every detection carries with it an implicit demand to explain what mechanism could sustain such radiance. Observers can measure flux and redshift, but interpretation requires models capable of reconciling the data with known physics. The brightest galaxy forces inquiry into processes that may be extreme versions of familiar mechanisms or entirely new phenomena concealed within the glare. The photons reaching Earth are not just evidence of distance. They are messengers of conditions so violent and so efficient at converting matter into light that even our best explanations strain against them. The recognition of this cosmic beacon does not close inquiry but intensifies it, pressing deeper into the relationship between light, gravity, and time. Each new dataset extends the puzzle, adding layers of complexity rather than resolution, leaving the impression that the galaxy is less an object captured than a riddle posed by the universe itself. At the center of extraordinary galactic brightness lies a paradox. The most radiant objects in the universe are powered by regions from which no light should escape. A supermassive black hole, by definition, allows nothing to cross its event horizon. Yet in its immediate surroundings, where gas spirals inward under irresistible gravity, energy release becomes so extreme that it outshines entire galaxies. This paradox is the essence of the quasar. The mechanism begins with accretion. Gas clouds, stellar remnants, and interstellar dust lose angular momentum as they approach the black hole, settling into a disk rotating at a significant fraction of the speed of light. In that disk, gravitational compression and frictional heating drive temperatures to millions of Kelvin. At such conditions, atoms are stripped of electrons, producing a plasma that radiates across the electromagnetic spectrum. What emerges is not starlight but a furnace of liberated gravitational energy, with efficiencies far exceeding nuclear fusion. If the Sun converts about 0.7% of mass into energy during fusion, matter falling into a black hole can release upward of 40% of its rest mass as radiation before crossing the horizon. The disparity explains how a single black hole, acting as a cosmic engine, can overwhelm the luminosity of billions of stars combined. Observations confirm the violent scale of this process. Quasars emit not only visible light but also X-rays and gamma rays, indicating acceleration of particles to relativistic speeds. Jets of plasma, collimated by magnetic fields, erupt from the poles, extending thousands of light-years into intergalactic space. These jets seed surrounding environments with energy and particles, shaping galaxy evolution in ways still being unraveled. Radio telescopes capture their vast reach, while X-ray observatories detect the shock waves as they plow into intergalactic gas. The quasar, then, is not a point of light but a multidimensional eruption, a system whose brightness is inseparable from violence. Human cognition struggles with such scales of violence expressed in light. Neuroscience offers parallels. When neurons fire in hypersynchronous bursts, as during epileptic seizures, the brain produces surges of energy far beyond ordinary patterns, often experienced as flashes of brightness or overwhelming sensations. In this sense, a quasar is to a galaxy what pathological oversynchronization is to a neural network, a catastrophic release that, paradoxically, manifests as illumination. Both involve an unstable concentration of energy that spills into perception, distorting the environment around it. The intensity of quasars has also shaped cultural imagination. When discovered in the 1960s, they were unlike anything previously catalogued. Some scientists initially hypothesized they might be white dwarfs, others speculated about exotic stars. Only with accumulating data did the scale become undeniable. These were galaxies whose cores blazed brighter than all else around them. The psychological reaction echoed earlier encounters with the infinite, fear mixed with wonder, disbelief tempered by calculation. Arthur Eddington had once called the stars the most brilliant factories in the universe. The quasar made stars seem provincial by comparison. To quantify such power, astronomers measure luminosity in ergs per second, a unit whose sheer scale detaches from daily intuition. A quasar can radiate 1047 ergs per second, while the Sun radiates 1033. The gap, 14 orders of magnitude, defies translation into sensory experience. Psychophysics studies show that human perception of intensity compresses logarithmically, meaning we register differences less than they are. In practice, no one can feel what a trillion-fold increase means. The mind collapses the gap into metaphor. Quasars become lighthouses, beacons, torches, language attempting to stretch perception to meet incomprehensible data. Behind the numbers lies the structure of the accretion disk. Its inner edge, near the event horizon, emits X-rays as matter falls into deeper gravitational wells. The outer regions glow in ultraviolet, heating surrounding gas until it radiates as broad emission lines. These lines, broadened by Doppler effects from extreme orbital speeds, carry signatures of turbulence, collisions, and relativistic motion. The spectrum of a quasar is not a simple fingerprint but a record of chaos, each line jagged with evidence of matter under maximum stress. Reading it requires not just instrumentation but models capable of linking turbulence, magnetism, and gravitation into coherent explanation. Experiments on plasma confinement in laboratories provide only limited analogies. Even in fusion reactors, conditions fall short of the extremes near a black hole. Yet lessons from these efforts, such as the role of magnetic reconnection in releasing bursts of energy, inform interpretations of quasar variability. Astronomers note that quasars flicker, brightness rising and falling over timescales from hours to years. These variations suggest instabilities in the accretion disk, like eddies in a river accelerating toward a cataract. Each flicker, when recorded, is a data point in the study of matter at the edge of collapse. The violence of quasars extends outward. Radiation pressure from their cores drives galactic winds, expelling gas and dust into surrounding space. This feedback regulates star formation. Too much energy, and the galaxy suffocates, stripped of material needed to form new generations of stars. The brightest galaxies, therefore, may also be the most destructive to themselves, their cores feeding so voraciously that they limit the life of their hosts. In this sense, brilliance carries a cost. What appears as radiance on cosmic scales often corresponds to depletion, a process mirrored in biology where hyperactive cells burn out their resources, leaving silence where once there was activity. Such feedback mechanisms are not merely theoretical. Observations of outflows reaching thousands of kilometers per second confirm that quasars alter their environments dramatically. Cold molecular gas, traced by carbon monoxide emissions, shows displacement from galactic centers, driven outward by quasar winds. These data suggest galaxies live in tension with their own cores, balanced between growth and disruption. Brightness, in this context, becomes a symptom of struggle, a signal that a galaxy is both alive with energy and at risk of consuming itself from within. The paradox remains unresolved. How can objects defined by their inescapable darkness generate light so overwhelming that it crosses billions of years? The answer, while grounded in physics, leaves open questions of scale, stability, and longevity. Each measurement sharpens the puzzle rather than resolves it, pressing inquiry toward ever more extreme interpretations of matter, energy, and perception. When astronomers attempt to describe the scale of quasar brilliance, they are forced into comparisons so vast that ordinary language falters. The measured luminosity of the brightest galaxies reaches into the realm of 10, 14, 10, 14 times the output of the Sun. This number does not describe a count of stars, but the effective power radiating from a single galactic core. To make sense of it, astrophysicists translate energy into solar equivalents, yet even this metaphor collapses under the weight of immensity. Hundreds of trillions of suns compressed into one radiant system remain beyond cognitive grasp. The human brain did not evolve to hold such magnitudes. Psychophysical studies have demonstrated that perception saturates at relatively modest scales. When exposed to light sources differing by large factors, subjects consistently underestimate the stronger source, compressing magnitude into manageable range. Stephen's power law formalized this tendency, showing that perceived intensity grows more slowly than actual physical intensity. At cosmic scales, the divergence becomes absolute. Numbers like 10, 14, 10, 14 are not merely underestimated but cognitively untouchable. What the data demand, the brain translates into awe, bewilderment, or silence. From the astrophysical perspective, the implications of such brightness are profound. Light traveling across billions of light-years retains enough intensity to be measured by sensitive detectors, meaning the original source emitted power on an unimaginable scale. For context, the Milky Way itself shines with about 10, 10, 10, 10 solar luminosities. A hyperluminous quasar exceeds this by factors of 10,000 or more. In effect, a single galactic nucleus projects energy equal to entire clusters of galaxies combined. These are not marginal outliers, but extreme events that reset the boundary conditions of what galaxies can become. Such luminosity reshapes surrounding environments. Radiation pressure from the quasar bathes its host galaxy, heating interstellar gas, ionizing atoms, and driving outflows at thousands of kilometers per second. Observations show that this feedback alters star formation rates, sometimes triggering bursts, sometimes suppressing them entirely. In the most extreme cases, quasar activity can strip a galaxy of the very material needed to sustain its brightness, initiating cycles of ignition and quiescence. The brightest galaxies, then, are unstable beacons, balancing precariously between creation and exhaustion. There is also the matter of cosmic distance. Light that left these galaxies billions of years ago reveals them as they were when the universe was still young. Their brilliance is not only a measure of power but of antiquity. Observing them is akin to examining fossils of energy, frozen snapshots of conditions long vanished. Yet because they are so luminous, they remain visible where lesser galaxies vanish into background noise. They serve as lighthouses of the early cosmos, guiding inquiry into epochs otherwise inaccessible. Their brilliance, paradoxically, illuminates not just themselves but the history of structure formation across cosmic time. In psychology, brightness has long served as a metaphor for awareness, yet its excess also provokes unease. Too much light blinds rather than reveals. Experiments on sensory overload demonstrate that overwhelming stimuli produce not clarity but disorientation, sometimes hallucination. Participants exposed to intense photic stimulation report patterns of geometric shapes, tunnels, or radiant fields that bear striking resemblance to descriptions of mystical visions. A quasar's brightness, though remote, invokes similar paradox. Light so great that it resists comprehension, generating images that are less about data than about altered states of mind. The parallel underscores how extremes in physical phenomena resonate with extremes in human consciousness. Historians of science note that each new threshold of magnitude unsettles existing frameworks. When supernovae were first recorded as stars that temporarily outshone planets, chroniclers interpreted them as omens. When galaxies beyond the Milky Way were recognized, their numbers overwhelmed previous cosmologies. The discovery of hyperluminous quasars extends this lineage, forcing reconsideration of how matter and energy can be organized. With each leap, the intellectual system strains to adapt, as though the cosmos continually offers challenges calibrated to the limits of thought. The numbers themselves become objects of contemplation. A luminosity of 10, 14, 10, 14 suns translates to about 10, 48, 10, 48 ergs per second. Over the span of a year, that energy release approaches 10, 55, 10, 55 ergs, equivalent to detonating billions of supernovae simultaneously. Such translation offers clarity, but also deepens the sense of disproportion. No local process, no volcano, no nuclear arsenal, no solar flare, approaches this domain. The only analogues are in imagination, where mythologies speak of eternal fires or radiant thrones, echoes of cognitive strategies to hold extremes by clothing them in narrative. The brightest galaxies also alter the intergalactic medium. Their radiation ionizes hydrogen across megaparsec scales, creating bubbles of transparency in otherwise opaque regions. This reionization effect carries consequences for the visibility of other objects, carving out windows through which the universe becomes more legible. Their light is not confined but spreads influence across cosmic neighborhoods, leaving signatures that persist long after the central engine quiets. In this way, their brilliance functions not only as a spectacle but as a tool, marking boundaries and reshaping environments beyond their own galactic confines. Brightness on this scale compels comparison with thresholds in human perception of power. Just as extreme light saturates the visual system, extreme sound saturates hearing, and extreme force saturates touch. In each domain, the nervous system ceases to encode proportionally, switching into protective modes of distortion or numbness. The quasar's brightness reveals a cosmic analog, the universe itself producing outputs so vast that observers cannot encode them proportionally, only indirectly, through instruments and translation. The gulf between emission and comprehension widens, yet the signal persists, demanding interpretation. As detectors grow more sensitive, more of these extreme objects emerge from obscurity. Each edition stretches theoretical models further, suggesting that the boundaries of brightness are not yet fixed. Somewhere in the unresolved depths of the cosmos, systems may burn even more ferociously, their photons still en route, waiting to reach the fragile apparatus of human detection. Behind the blinding nucleus of a hyperluminous galaxy lies the question of structure. What kind of host can sustain such intensity without collapsing into silence? To answer this requires turning attention away from the glare of the core and toward the galactic body that surrounds it. Though often overshadowed by the radiance of the quasar, the host galaxy carries the material, dynamics, and scars that make such brightness possible. The first challenge is visibility. The nucleus overwhelms the host, drowning starlight in torrents of radiation. Even the most advanced optical telescopes struggle to detect faint stellar halos when the central engine dominates the image. Astronomers address this by shifting to longer wavelengths, where dust re-emits absorbed radiation, or by employing interferometry to disentangle core emission from surrounding structures. Such techniques have revealed that many hyperluminous galaxies are not orderly spirals or smooth ellipticals, but chaotic assemblages marked by collision, merger, and disruption. Galaxy mergers appear central to the story. When two massive galaxies collide, their gas reservoirs are driven inward under gravitational torques, compressing into dense clouds that fuel both starbursts and black hole growth. Observations of the brightest systems show tidal tails, warped disks, and disturbed morphologies, evidence of violent interactions. Simulations confirm that such encounters funnel matter into central regions efficiently, feeding accretion disks at rates sufficient to ignite quasars. Brilliance, in this sense, is the aftermath of violence. The light we see is the residue of galaxies tearing themselves apart to create something temporarily more radiant. The surrounding medium provides further clues. Molecular gas, traced through emissions of carbon monoxide, indicates enormous reservoirs concentrated near galactic centers. Some hyperluminous systems contain billions of solar masses of cold gas, an abundance that can sustain both star formation and accretion simultaneously. Yet this abundance is unstable. Outflows driven by quasar winds eject material at high velocities, reducing the very fuel that powers the luminosity. Observations capture this tension. Inflows channel gas inward while outflows drive it outward, producing a dynamic equilibrium that sustains brilliance for limited epochs. Dust plays a critical role in shaping what is observed. Radiation from the nucleus is absorbed and re-emitted by dust grains at infrared wavelengths, producing spectral energy distributions with pronounced peaks. This re-radiated light constitutes much of the observed luminosity, meaning the brightest galaxies often appear as luminous infrared galaxies, their visible light hidden behind veils of dust. Instruments such as the Spitzer and Herschel space telescopes have mapped these emissions, revealing that obscuration is not peripheral but central to hyperluminous systems. Dust both hides and magnifies, concealing stellar populations while re-radiating nuclear energy into new spectral domains. The stellar component, though faint against the glare, is no less significant. Analysis of spectral absorption features reveals that many host galaxies harbor old stellar populations, relics of earlier epochs, alongside bursts of new star formation triggered by mergers. This coexistence suggests that hyperluminous phases are transient overlays on otherwise long-lived galaxies. A galaxy may spend billions of years in quiet evolution, only to ignite briefly into quasar brilliance when conditions align. The host, then, is not obliterated by brightness but transformed by it, accumulating scars that persist long after the core dims. Psychological metaphors emerge naturally here. Just as human identity is not reducible to moments of crisis or ecstasy, galactic identity cannot be captured by transient luminosity alone. The host galaxy, with its billions of stars, carries the continuity of existence, while the quasar phase represents an episode of extreme energy release. Neuroscientific studies of altered states, whether induced by seizures, psychedelic compounds, or sensory overload, show that moments of intense brightness or intensity do not erase the underlying neural architecture. Instead, they imprint traces, leaving the network changed but not annihilated. Galaxies mirror this principle, bearing luminous episodes as transformations inscribed into their structures. The scale of these transformations becomes evident when studying feedback. Quasar-driven winds and jets not only reshape the host galaxy, but also extend into intergalactic space, enriching the medium with heavy elements. Observations of distant quasars show that their outflows carry metals into regions far beyond the galaxy itself, altering the chemistry of cosmic filaments. The host is not an isolated system, but a node in a larger web, and its brilliance radiates influence beyond its own confines. In this sense, the brightest galaxies are engines of cosmic change, their excess energy reorganizing matter on scales that surpass their visible boundaries. Detecting these structural signatures requires patience and precision. Adaptive optics correct for atmospheric distortion, while interferometric arrays combine signals from multiple telescopes to increase resolution. Each improvement peels away a layer of glare, revealing faint arcs, distorted halos, or star-forming knots hidden behind the quasar light. What emerges is not a single archetype but a diversity of hosts, some compact and spheroidal, others irregular and sprawling, each bearing evidence of tumult. These forms testify that brilliance is not a product of equilibrium but of imbalance, where collisions, inflows, and instabilities converge. The unresolved question is longevity. How long can a galaxy sustain luminosity at such extremes before exhausting its fuel or destabilizing its structure? Estimates suggest quasar phases last between 10 and 100 million years, a brief episode on cosmic timescales. If so, then the brightest galaxies we observe are snapshots of transience, caught during rare intervals of heightened activity. The hosts themselves endure across billions of years, but the glare of their cores represents a fleeting condition, one that cannot be permanent without destroying the system that sustains it. This impermanence deepens the enigma. If hyperluminous phases are rare and short-lived, why do we detect them across vast stretches of sky? Does their frequency imply that conditions for ignition are more common than models predict, or that their brightness allows them to dominate observations despite their scarcity? The tension between rarity and visibility remains unresolved, pressing inquiry toward improved surveys, deeper instruments, and new frameworks of interpretation. The hosts of these galaxies, partially hidden yet essential, embody the contradiction of brilliance sustained by fragility. Their distorted forms, their obscuring dust, their unstable reservoirs of gas, all point toward systems living on the edge of collapse. The evidence suggests that every measure of brightness conceals a story of conflict, imbalance, and eventual transformation still awaiting full decipherment. The light of hyperluminous galaxies is not merely a spectacle of physics, but also a probe of cosmic time. Each photon that reaches a detector carries with it the memory of an epoch long past, traversing billions of years of expansion before entering human instruments. The galaxies that shine most brightly tend to be located at immense distances, which means their light began its journey when the universe was a fraction of its present age. Their brilliance, while extraordinary in absolute terms, is also a consequence of visibility. Only the most radiant systems pierce the cosmic fog of antiquity. Cosmic redshift encodes this antiquity. As space expands, wavelengths stretch, moving energy from ultraviolet into infrared, from infrared into millimeter, until only specialized detectors can record it. The observed spectrum is a palimpsest of two histories: the intrinsic emission of the galaxy and the subsequent distortion imposed by cosmic expansion. Separating these histories requires careful modeling, disentangling local processes from universal dynamics. When this is accomplished, astronomers can place the galaxy within a timeline, locating its emission billions of years before the formation of Earth. These timelines converge on the early epochs of structure formation. Observations reveal that many hyperluminous quasars flourished during the first few billion years after the Big Bang, a period when galaxies were still assembling from primordial gas. The fact that supermassive black holes had already grown to billions of solar masses at such early times presents a challenge to theoretical models. Conventional accretion rates appear insufficient to reach these scales so quickly, suggesting either episodes of super-Eddington growth or the existence of massive initial seeds formed by direct collapse of primordial gas clouds. Each possibility reshapes understanding of how quickly complexity emerged in the cosmos. The role of these galaxies in cosmic reionization is equally critical. After the Big Bang, the universe cooled into a neutral state, with hydrogen atoms absorbing most radiation and rendering space opaque to ultraviolet light. At some later epoch, ultraviolet photons from the first luminous sources reionized hydrogen, making the universe transparent again. Hyperluminous quasars, with their enormous ultraviolet output, are prime candidates for agents of reionization. Observations of absorption lines in the intergalactic medium reveal ionized bubbles surrounding such galaxies, evidence that their radiation carved out zones of transparency. Yet the balance of contribution between quasars and star-forming galaxies remains unsettled, leaving open the question of which sources transformed the universe into its present transparent state. The scale of these bubbles is striking. Some extend millions of light-years, encompassing volumes larger than present-day galaxy clusters. Within them, hydrogen atoms are stripped of electrons, creating plasma regions that allow subsequent light to propagate more freely. Such transformations are not localized events but cosmic engineering, shaping the medium through which all subsequent galaxies became visible. The brightest galaxies, by virtue of their intensity, played roles far disproportionate to their numbers, altering the conditions of visibility for everything that followed. The psychological resonance of this transformation is profound. To contemplate epochs when light could not travel freely is to confront a universe hidden from itself, a cosmos where brilliance was born into suffocation until certain sources tore open transparency. In cognitive terms, this parallels the developmental thresholds of consciousness, when neural activity reaches critical integration and awareness emerges from opacity. Just as infant brains pass from fragmented perceptions into cohesive awareness, The cosmos passed from opaque infancy into a transparent stage illuminated by its most luminous actors. The analogy, while metaphorical, highlights the continuity of concepts across scales. Thresholds of brightness are thresholds of revelation. Data from the most distant quasars indicate that some existed less than 1 billion years after the Big Bang. Their light, redshifted to extreme degrees, pushes the limits of current instruments, requiring facilities such as the James Webb Space Telescope to disentangle. These detections challenge assumptions about time available for black hole growth and galaxy assembly. If systems so luminous already existed at such early epochs, then the pathways to complexity must be shorter and more violent than anticipated. Models of gradual accumulation falter in the face of objects that demand rapid, efficient formation mechanisms. Uncertainties multiply as distances increase. Absorption by intergalactic hydrogen leaves imprints known as the Gunn-Peterson trough, regions of spectrum devoid of light where neutral hydrogen absorbs completely. The detection of such troughs near quasars signals that their light traveled through environments still transitioning from opacity to transparency. Each spectrum becomes a record not just of the galaxy itself, but of the surrounding universe in transformation. To read these spectra is to reconstruct the timing and geography of cosmic dawn, an enterprise requiring both precision measurement and theoretical imagination. Even the brightest quasars are not uniform. Variability on timescales of days to months suggests that accretion flows in the early universe were turbulent, unstable, and perhaps intermittent. This variability complicates efforts to use them as standard candles, but enriches their value as laboratories of extreme physics. Fluctuations in brightness reveal processes on scales of light days, implying compact emission regions despite the vastness of the systems involved. To capture such flickering across billions of years stretches both instruments and interpretive frameworks, yet each fluctuation encodes dynamics at the edge of black hole horizons in epochs otherwise lost to time. What emerges is a picture of the early universe where brilliance and obscurity intertwined. Galaxies still forming from collapsing gas clouds already housed cores blazing with energies that reshaped their neighborhoods and pierced cosmic opacity. Their visibility across cosmic time makes them both outliers and essential guides, anchoring reconstructions of history in data rather than conjecture. Yet the mechanisms that permitted such rapid assembly remain only partially explained, leaving questions that press against the current frontier of astrophysical theory. The discovery of each new hyperluminous galaxy at extreme redshift intensifies this tension. Their existence demands conditions that theory struggles to provide, hinting that either unseen processes operated in the early universe or that existing frameworks are incomplete. Each observation becomes less a resolution than an opening, pointing to gaps where the unknown exerts pressure on the known, and where the next measurement may shift the balance between comprehension and mystery. To understand the extremes of hyperluminous galaxies requires probing the physics that governs their central engines. The key lies in the processes that occur within the accretion disk, where matter falling toward a supermassive black hole is transformed into radiation. Although the broad outlines are established, the detailed mechanics remain uncertain, with competing models struggling to capture the turbulence, magnetism, and relativistic dynamics that shape these environments. The first principle is that energy release arises from gravitational potential. As matter spirals inward, it loses orbital energy, which must be dissipated as heat and radiation. The viscosity that enables this loss is not molecular, but magnetic in origin. Magnetorotational instability, a mechanism identified in the 1990s, is now considered central to accretion. Weak magnetic fields, when embedded in differentially rotating plasma, amplify through feedback loops, creating turbulence that transfers angular momentum outward and mass inward. Without this instability, disks would stall, unable to shed angular momentum. With it, accretion flows become chaotic and luminous, capable of driving the radiative intensities recorded by telescopes. Within such disks, Temperatures span extreme ranges. Inner regions reach millions of Kelvin, producing X-rays, while outer regions emit in ultraviolet and optical bands. This stratification is not static. Fluctuations propagate through the disk, leading to variability in observed brightness. The coupling of magnetic turbulence and radiation transport produces instabilities that can trigger sudden surges or drops in luminosity. On human timescales, these may appear as flickers, but they represent vast reorganizations of energy flow in regions spanning light years. Jets represent another dimension of the problem. Many hyperluminous systems exhibit relativistic outflows extending tens of thousands of light-years. The origin of these jets remains contested. Leading models invoke the extraction of rotational energy from the black hole itself, a process described by the Blandford-Znajek mechanism. In this framework, magnetic field lines anchored in the accretion disk thread the event horizon, twisting under frame dragging and launching plasma outward at near-light speeds. The efficiency of this process suggests that not only matter but also spacetime curvature contributes to luminosity, turning the black hole into a generator. The interaction of jets with surrounding gas produces secondary luminosity. Shocks heat the medium, creating radio lobes visible across millions of years. These structures serve as archaeological records of galactic activity, revealing histories of outburst and quiescence. The symmetry and scale of such lobes indicate that hyperluminous phases may repeat, with black holes cycling through active and dormant states. Each cycle leaves imprints far larger than the galaxy itself, embedding luminous episodes into the fabric of intergalactic space. Another unresolved issue concerns the limits of accretion. The Eddington limit defines the balance point where radiation pressure outward equals gravitational pull inward. Exceeding this should expel infalling matter, choking off accretion. Yet evidence from hyperluminous quasars suggests super-Eddington flows are possible. Models propose that in thick, radiation-dominated disks, energy escapes preferentially along polar funnels, allowing inflow to continue despite high luminosity. If confirmed, this mechanism explains how supermassive black holes grew so rapidly in the early universe, but it also implies a regime of physics not yet fully understood. The complexity deepens when relativistic effects are considered. Near the event horizon, spacetime curvature alters trajectories of photons, bending light into arcs and loops. General relativity predicts that radiation can orbit the black hole multiple times before escaping, producing distorted spectra. Time dilation stretches variability signals, complicating interpretation. Instruments capable of measuring polarization provide additional constraints, revealing that magnetic fields near horizons are ordered rather than random, consistent with jet launching models. Yet the full geometry of these regions remains hidden, glimpsed only through indirect signatures. Human cognition encounters limits when faced with such abstractions. Studies of mental imagery show that individuals can maintain stable pictures of three-dimensional objects, but distortions of spacetime defy visualization. To grasp frame dragging or photon orbits requires mathematical formalism, not intuitive imagery. This disjunction produces a sense of estrangement. Data are precise, but comprehension is fragmentary. The brightest galaxies embody this estrangement, presenting observations that are measurable yet conceptually elusive, pushing the brain to operate at the edge of its symbolic capacity. Laboratory analogues provide partial insight. Plasma physics experiments reproduce instabilities and reconnection events similar to those expected in accretion disks. High-powered lasers compress matter to densities where radiation pressure becomes significant. These controlled settings offer glimpses of processes operating on galactic scales, though always with differences of magnitude too vast to bridge completely. The effort underscores the principle that astrophysics is both empirical and experimental by proxy, building universes inside machines to approximate conditions no human could otherwise approach. The unresolved character of accretion physics leaves consequences for cosmology. Predictions of black hole growth, feedback strength, and galaxy evolution all depend on how efficiently matter is converted into light. If efficiencies are higher than assumed, fewer accretion events are needed to explain hyperluminous systems. If lower, then hidden populations of bright galaxies may exist beyond current detection. In either case, the physics of the disk propagates outward into questions about the census of galaxies, the history of cosmic light, and the structure of the universe itself. As instrumentation improves, more direct observations press against these theoretical uncertainties. Very long baseline interferometry now resolves event horizon scale structures, revealing asymmetric brightness consistent with relativistic beaming. Future missions promise to extend this technique to higher frequencies, mapping not only nearby black holes but also luminous systems across cosmological distances. Each refinement sharpens the tension between model and reality, as details emerge that cannot be reconciled without revising the underlying physics. The brightest galaxies, by forcing the limits of theory, become crucibles where both astrophysics and human cognition are tested. Their spectra, variability, and morphology all demand interpretations that stretch beyond conventional frameworks. The confrontation is not merely technical but conceptual, as each new measurement carries implications that destabilize prior confidence. The unresolved nature of their engines leaves a sense of incompleteness, with every observation sharpening questions rather than resolving them. The influence of hyperluminous galaxies extends far beyond their own structures, reshaping the cosmic environment that surrounds them. Their radiation, winds, and jets inject energy into space on scales that rival the largest structures known, creating effects that ripple through intergalactic filaments and alter the architecture of galaxy clusters. To examine these galaxies only as isolated beacons is to miss their role as engines of environmental transformation. One of the most direct expressions of this influence is mechanical feedback. Jets driven at relativistic speeds slam into intergalactic gas, inflating cavities detectable in X-ray surveys of galaxy clusters. These cavities, sometimes spanning hundreds of thousands of light-years, testify to the energy released during active phases. The energy input can suppress cooling flows that would otherwise form stars, delaying or preventing further condensation of matter. In this sense, hyperluminous galaxies impose order on their surroundings, regulating the pace at which other galaxies develop. Yet the order imposed is not gentle but violent, sculpted by shock fronts, turbulence, and thermal upheaval. Radiative feedback is equally consequential. Ultraviolet and X-ray photons ionize hydrogen across vast regions, stripping electrons and altering the thermal history of the intergalactic medium. This process changes the transparency of cosmic filaments, affecting how light from even more distant sources reaches observers. A hyperluminous galaxy, by radiating far beyond its boundaries, alters the visibility of the universe around it. For astronomers, such galaxies serve as both windows and filters, their light enabling detection of intervening matter while simultaneously reshaping it. The chemical consequences of these processes are extensive. Winds driven from galactic cores carry heavy elements synthesized in stars and supernovae into the intergalactic medium. Measurements of absorption lines in quasar spectra reveal traces of carbon, oxygen, and silicon at distances where no stars should yet have formed locally. These elements must have been transported by outflows from early hyperluminous systems, enriching otherwise pristine gas. The enrichment process links the brilliance of quasars to the eventual conditions for planet formation, embedding the physics of extreme galaxies into the prehistory of habitable worlds. The distribution of matter across cosmic scales is also affected. Computer simulations incorporating feedback from luminous galaxies demonstrate that without their energy input, clusters would overproduce stars and gas densities would grow unrealistically high. By expelling material, quasars prevent runaway growth, shaping the large-scale structure into the forms observed today. The sharp contrast between voids and filaments owes part of its clarity to these expulsions, which carve emptiness in some regions and compress matter in others. Brilliance is therefore not only a local phenomenon, but an architect of cosmic geography. From the perspective of perception, the scale of this influence induces dissonance. Human cognitive frameworks evolved to register cause and effect in proximal environments, not across millions of light-years. To accept that radiation from a distant galactic core can alter the chemistry of regions never touched by its stars is to confront a causal reach so extended it defies intuition. Cognitive scientists studying mental models of scale note that when confronted with distances and times far beyond experience, individuals default to metaphor or narrative, translating abstract dynamics into stories of influence, contagion, or dominance. The language of cosmic feedback often echoes these patterns, framing galaxies as actors exerting will, even when the underlying processes are strictly physical. Observational data reinforce the magnitude of this reach. Instruments such as the Atacama Large Millimeter/Submillimeter Array detect outflows of molecular gas moving at thousands of kilometers per second, carrying tens of billions of solar masses into intergalactic space. These outflows are not transient breezes, but sustained expulsions capable of altering galactic evolution permanently. In some systems, more gas is driven out than remains to form stars, suggesting that brilliance hastens depletion, accelerating a galaxy's trajectory toward dormancy. Each hyperluminous phase, while radiant, carries within it the seeds of its own diminishment. The paradox of creation through destruction runs through these dynamics. By heating, ionizing, and expelling matter, quasars appear to inhibit the growth of their host galaxies. Yet the same processes distribute metals, maintain balance in clusters, and prepare the medium for subsequent generations of structure. Destructive energy becomes constructive in larger context, a duality that resists simple categorization. Psychologically, such dualities echo patterns in human experience where trauma or disruption catalyzes new forms of order, forcing adaptation beyond previous limits. The cosmos, through its brightest galaxies, enacts similar transformations across incomprehensible scales. Measurements of the Sunyaev-Zeldovich effect, in which quasar-driven electrons scatter photons of the cosmic microwave background, provide further evidence of influence. By distorting relic radiation from the Big Bang, luminous galaxies write themselves into the oldest observable signal. This coupling between early universe light and later galactic brilliance creates a layered record, where present extremes reach backward to alter ancient imprints. Each detection of such distortions underscores how far-reaching a single hyperluminous phase can be, blending with the most fundamental background of cosmic history. Despite these insights, uncertainties remain about how widespread such feedback truly is. Some galaxies exhibit dramatic outflows while others, equally luminous, seem more quiescent. The reasons for this diversity are not yet clear. Orientation, magnetic field configuration, or differences in accretion flow may determine whether energy escapes violently or remains trapped. This diversity complicates attempts to model large-scale evolution, as it suggests that hyperluminous phases are not uniform engines but varied, contingent, and perhaps chaotic in their influence. Each unresolved detail leaves open questions about the balance of cosmic energy. How much of the structure visible today owes its form to the brilliance of ancient quasars? How many voids, clusters, and filaments carry scars of feedback written in their densities and temperatures? The data accumulate, yet the interpretation remains unsettled, with every discovery expanding the horizon of uncertainty. The brightest galaxies stand not only as objects of study, but as forces whose consequences stretch across the universe, shaping landscapes still only partially mapped. The most luminous galaxies press directly upon questions of cosmic order and instability. Their outflows, radiation, and gravitational dynamics do not simply act upon their local surroundings, but ripple into the deepest frameworks used to describe how matter and energy are organized across the universe. In their extremes, they highlight the tenuous balance between forces that sustain structure and those that dissolve it. At the scale of galaxy clusters, the disruptive influence of hyperluminous systems complicates thermodynamic equilibrium. Hot intracluster gas emits X-rays as it cools, which should lead to dense cores where new stars form. Yet observations reveal that star formation rates are often suppressed. The missing ingredient is energy injection from luminous galactic nuclei, which heat the medium and prevent collapse. This balance is precarious, oscillating between cooling inflows and reheating outbursts. Astronomers detect cycles in which cavities blown by jets collapse, inflows resume, and new outbursts reignite, suggesting that instability is not accidental but fundamental to how clusters evolve. On larger scales, the presence of hyperluminous quasars disrupts assumptions about uniformity. The cosmological principle posits homogeneity and isotropy at sufficient scales, but surveys reveal localized excesses of brightness, quasar clusters extending across hundreds of millions of light-years. These concentrations, sometimes called quasar groups, exceed expected statistical variance, hinting at structures larger than standard cosmology predicts. If such structures are genuine, they may challenge the notion that matter is evenly distributed when averaged over great distances. The brightest galaxies become markers of possible fractures in the very principle of cosmological symmetry. The issue of time deepens the challenge. Hyperluminous systems that appear at early epochs suggest that complexity emerged faster than models permit. If black holes reached billions of solar masses within a few hundred million years, then either matter collapsed into seeds of exceptional mass or accretion proceeded at efficiencies beyond known physics. Both options destabilize current frameworks. The former implies direct collapse models with minimal fragmentation, while the latter demands super-Eddington processes that evade radiation pressure limits. Neither pathway is fully reconciled with simulations, leaving the early universe more unstable in theory than its observations imply. Instability also arises in the statistical interpretation of brightness itself. The luminosity function of quasars, mapping how many exist at different brightness levels, shows a steep decline at the highest luminosities. Yet discoveries of individual outliers repeatedly exceed expectations, extending the tail further than predicted. Each new detection forces recalibration, suggesting that the universe harbors more extremes than anticipated. In probability terms, the distribution of brilliance appears to resist convergence, as if the cosmos sustains conditions for rarity more frequently than mathematics would dictate. The psychological resonance of this resistance is notable. Human cognition relies on patterns converging toward stability, with exceptions confined to manageable bounds. When outliers multiply, confidence in models diminishes, evoking unease akin to vertigo. Studies in cognitive psychology show that when individuals encounter anomalies too frequent to ignore yet too extreme to integrate, they experience heightened stress responses, often accompanied by a compulsion to reframe the entire system of understanding. Hyperluminous galaxies function in this way for astrophysics. Their existence compels re-evaluation of the very rules meant to contain them. Observational anomalies intensify the unease. Some quasars exhibit brightness variability so rapid it contradicts size constraints imposed by light travel times, implying emission regions smaller than models allow. Others show spectral lines shifted and broadened beyond expectations, as if gas near the black hole is moving at velocities that exceed calculated limits. Instruments record these deviations without ambiguity, yet theoretical frameworks hesitate, oscillating between explanations that invoke exotic physics and those that attribute discrepancies to observational bias. The persistence of anomalies across independent observations undermines the latter option, leaving the field suspended between certainty of data and uncertainty of interpretation. The role of dark matter adds another layer of instability. Hyperluminous galaxies do not exist in isolation, but within massive halos whose properties influence gas infall and feedback efficiency. If halos are more massive than anticipated, they provide reservoirs for sustained accretion. If less massive, then current models overestimate the capacity for growth. Measurements of lensing distortions around these galaxies suggest concentrations of dark matter that do not always align with expectations from simulations. In some cases, halos appear more compact, in others more diffuse, hinting that feedback from luminous phases may reshape dark matter distributions themselves. If verified, this would imply that baryonic processes, though negligible in mass compared to dark matter, can still perturb its structure through violent energy release. Cosmological simulations attempt to incorporate these instabilities, but the parameter space grows unmanageable. Feedback strength, accretion efficiency, merger frequency, and halo mass must all be adjusted to reconcile data, yet the adjustments often contradict each other. The result is a tension between fidelity to observation and coherence of theory. Physicists accustomed to elegant frameworks find themselves navigating a terrain where brilliance destabilizes elegance, and where each refinement opens further contradictions. The unresolved nature of these tensions transforms hyperluminous galaxies into crucibles of cosmological theory. They are not merely luminous markers at great distances, but pressure points where current models reveal their fragility. Each observation sharpens the contrast between the apparent order of the universe and the instability that underlies it. The brightest galaxies illuminate not only space but also the fractures in human attempts to describe it, pressing inquiry toward domains where certainty dissolves into provisional conjecture. The persistence of these uncertainties leaves an atmosphere of anticipation. Every new survey, every spectrum, every outburst measured carries the possibility of extending the instability further, forcing yet another recalibration. The brightest galaxies continue to resist containment within familiar boundaries, and each unresolved discrepancy leaves open the prospect of deeper shifts yet to come.